So the heart of algebra has 5 kind of main groupings of content. We're going to start with fluency in solving linear equations, linear inequalities, and systems. That's technically lesson 4. But I wanted to do it first because it's solving all those things without word problems. It's just, hey, here's this equation, solve it. Here's this inequality, solve it. Okay? Then lessons 1, 2, and 3 will go back through those same topics, but break it up into our applications, our context, our word problem. All right? And then lesson 5, we're going to be looking at some relationships between linear equations, the coordinate plane, their graphs, so kind of comparing equations and graphs and different things that represent the same context. Okay? We'll get probably about halfway through lesson 4 today. We'll finish it up tomorrow. So the main objective with lesson 4 is that you'll be able to solve linear equations, linear inequalities, and systems of linear equations without a context. So we have some pretty just straightforward equations. There's going to be a few steps, but for the most part, we should be pretty familiar with these. I'm going to roll through the first one. The second one, I'm going to talk about some tricks that kind of speed it up a little bit to make it a little bit easier, especially if this type of question shows up on a non-calculated portion. And then the next 2 examples have some special answers, so we'll look at those too. So I have this big, long equation. What's the first thing I should do to clean this up? Distribute. Always get rid of your groupings first. So we'll use our distributive property and rewrite our equation. Once our grouping's done, and we've dealt with all of those, we don't have any exponents, any radicals, any absolute value, and we're just left with a long list of terms, then we can go through our combining like terms. Start with one side at a time. If I have a negative 5x and a 3x, what do those combine to? Negative 2x. And then I have negative 5 and 2, negative 3. And then on the right side, there are no like terms. So we can just rewrite the right side. Now, once we're down to one variable on each side, then we want to group our variables together to the same side. You can either add 2x to both sides or subtract 6x. It doesn't matter which one you do, but you want to probably move the smaller number so that your coefficient ends up being positive. If you subtract 6x, you'll end up with the same answer. You're just going to have to deal with a negative later, and the more negatives we have, the more likely we have for a sign error. So try and make sure that you're moving the smaller value with the with the variable to the other side. Negative 2 plus 2 gives me 0, which is why that goes away. And then now that we're down to one variable, our goal is to get everything away from the variable. So am I going to get rid of the 8 or the 4 first? The 4. Always undo your subtraction, and then coefficients will be last. So we'll subtract 4 to get 0 and negative 7. And then how do I separate a coefficient from its variable? Divide. As long as your fraction, if you divide it, is a terminating decimal, then decimals are fine. But if you don't need to, I don't see the point in turning that into a decimal because you can use fractions. Okay? Negative 7 over 8. Note that if you end up with an improper fraction and it's a student-filled response, okay, those little bubbles that you have to do at the end, leave it improper because otherwise it'll misinterpret your answer. For example, if you had 3 over 2 as a fraction and you rewrite that as 1.5, then you go to put it into your student response where you've got your boxes, right? And you try to put in 1.5, you're going to put in 1, 1/2, which they're going to read as 11 over 2. Totally different answer. Okay? So no mixed numbers on the SAT, only improper fractions. Or you can write it as a decimal. Okay? As long as it's not a repeating decimal. So if you have something with a denominator of 3, well, sorry, you're going to have to leave it as a fraction. Okay? Now, here we've got some distributive property. We'll clean that up again, just like we did last time. Take care of that. Negative 6x plus 4.8 equals negative 9x plus 7.2. We did our distributive property. Now, we can do the same exact steps that we did here. We can add 9x to both sides. We can subtract 4.8 for both sides. Divide by our coefficient. Okay? And that's fine. But sometimes when we have decimals, and especially when we have fractions, it's going to be much more efficient for us to get rid of our decimals. Okay? Efficiency is key. When you've got anywhere from a minute to 2 minutes to answer each question, you can shave on a fluency question is more seconds you can use on a context problem where you might need to have critically about the question and what it's asking for. Okay? So when we have decimals, you can multiply your entire equation by some power of 10. 10, 100, 1,000, 10,000. And that's going to clear out the decimals. And you're going to multiply by a power of 10 based on the number of digits you have behind your decimal. So because these both have only one digit, I can multiply both sides of my equation by 10, and that's going to get rid of that decimal point. Because 4.8 times 10 is 48. 7.2 times 10 is 72. If I had the number 4.08, I would need to multiply by 100 because I've got 2 digits after the decimal. 4.081 would require 1,000 with 3 digits after the decimal. And then we can follow our same process that we've been doing. Oops, that should be a 90. Okay. Add 90 to both sides. Subtract 48 from both sides. Divide by our coefficient. And then simplify your fraction. Same exact process. Okay, the only thing that we added in was that multiplication by a factor of 10 that helps get rid of that fraction or that decimal. If you didn't do that, it's fine, but you're going to end up doing it eventually anyway. Because what will happen is if you left this the way it was, instead of multiplying by 10, and you go through to solve, you're going to end up getting x equals 2.4 over 3. Okay? A decimal, as your numerator or denominator, does not qualify as a simplified fraction. So we're going to have to get rid of that decimal. How do we get rid of the decimal? Multiply it by 10, which turns it into 24 over 30. And now we're back here already. And then we got to simplify it. So it's a matter of take care of it now or take care of it later. Either way, you'll get to the right answer, but you need to make sure your fraction is completely simplified. Any questions on either of those two? If I had worked this part out without multiplying by 10, you end up getting 2.4 over 3. That's what it ends up working. All right. What I want you to do is take 2 or 3 minutes, and I want you to start both of these. Okay? These are going to give us some very specific and unique answers, different compared to the last two. Okay? So go ahead and start working through both of those. Just a couple minutes. I don't expect you to necessarily finish in that time, but I want you to get started and kind of see if you recognize a pattern. 2 steps in, you should start to see something special. Okay? When I look at this question on the right, on the left, if I take a number, x, and I multiply it by 3, then subtract 9, will that ever give me the same answer as if I take that number and multiply it by 3, but instead subtract by 17? No, it won't. There's no number where I could say, okay, let me subtract 9 and let me subtract 17 and get the same thing. It's never going to work. Okay? So here we should notice that something's off. If we continue with the process algebraically, we see why we end up with something weird. I subtract 3x so that I can try and combine everything, but it equals 0 on both sides. So I'm left with negative 9 equals negative 17. That will never be true. Negative 9 will never equal negative 17. So this means it doesn't matter what number you plug in for x, it's never going to be a true statement. No solution. Okay. We call this a contradiction. Okay? It's a contradiction. We have no solution. There is no value of x that would satisfy this equation and make it true. And once we kind of reach this point, we don't really need to go any further. We can recognize that as a contradiction. Our variable term is identical on both sides, but our coefficient is different. I'm sorry, not our coefficient, our constant. Our variable term is identical on both sides, but our constant is different. If that ends up being the case, well, we're going to end up with a contradiction, and we can verify it algebraically. What do we notice on the right? They're the same. Okay? So if we continue the same thought process that we did here, okay, no matter what value I plug in for t, on both sides, I'm going to be multiplying by negative 3 and then subtracting by 10. So I can plug in a 1, I'll get the same answer. I can plug in a 5, I'll get the same answer. Negative 10, I'll still get the same answer. So here we have infinitely many solutions. Other ways that we could say it, all real numbers. Or we could use the set symbol for all real numbers. Or we could use interval notation and state that our solution is in the range of negative infinity to infinity. We call this an identity. And if we were to continue it algebraically, because maybe you're just working furiously and you don't stop there, you just keep going. Okay, well, you want to know if you get to the end, what's going to happen. Well, same thing, I add 3t to both sides. Those cancel out, giving me 0. And I'm left with negative 10 equals negative 10. I'm left with a true equation statement. This number equals this number. Well, yeah. And it doesn't matter what number it is. It could be 0 equals 0, 5 equals 5, 12 equals 12, whatever. This number equals this number. There's no more variables. As long as it's true, we have an identity. Identities have infinitely many solutions. But recognizing that both sides of the equation are equivalent while we still have the variables is an important process for identifying those types of systems. Okay? Questions on that? Yeah.
Which of those terms was the...
I've seen that most common.
So if we automatically see those two sides are the same, we just think of this.
All right. We'll do these and then we'll take a break for today. So I have fractions and I have decimals. I don't like fractions and I don't like decimals. They're annoying. Okay? But that's part of life. Okay? Fractions in everything. Decimals in everything. All right? But there's some shortcuts that allow us to kind of circumnavigate that and get rid of them. All right? We dealt with decimals a little bit. We'll do it again in a moment. but let's look at our fractions first. Okay? Normally, in order to add fractions, what do we have to have? Okay? So we're going to think along that same train, but I'm not actually going to change the fraction of the common denominator, but I'm going to use it. Okay? So looking at my denominators of 2 and 5, what is my least common denominator going to be? 10. So I'm going to use that 10. And then what I'm going to do instead is I'm going to multiply everything by that least common denominator, and that's going to do the nice little magic trick of making my denominators disappear when we simplify. So to start, let's just get rid of this pesky parentheses because, you know, it's annoying. And then we're going to go ahead and multiply all of our terms by 10. So I'm going to multiply 3 halves by 10. Well, that gives me 30 over 2. I'm going to multiply 3y by 10. That gives me negative 30y. I'm going to multiply 3/5 by 10 to get 30 fifths. And 15y by 10 to get 150y. And this is where the magic trick comes in. What's 30 over 2?
15.
What's 30 over 5?
6.
And then now we can go through our normal algebraic process. Combine your variables, isolate. So let's add 30y to both sides. Subtract 6. Divide by our coefficient. And then simplify our fraction. Much less painful to solve when we don't have fractions anymore. Much less painful to solve. You can still do it. You'll still get 1/20. It's just going to take you a little longer. So with decimals, we talked about multiply by a power of 10. So if I've got 0.05 and 0.12, what should I multiply by that's going to get rid of that decimal? 100. 2 digits, 2 zeros. Okay? So I'm going to multiply by 100. And you're going to do it, you're going to multiply by whatever the longest decimal is. If I had 0.05 and then 0.121, well then I have to multiply by 1,000 because the longest decimal is 3 digits. Okay? So whichever the longest one is. Now, this one I did distributive property first before I multiplied. I'm going to show this one without doing distributive property first. It'll still work. Just note that this is a term. That is considered one term. And then this is a term. So we're going to multiply everything by 100. Okay? 100 times 0.05 is 5. 100 times 0.12 is 12. That term already got multiplied by 100. So the x and the 5,000 don't change. Okay? The x and the 5,000 don't change because I already multiplied that term by 12. And then 9,000 or 94,000 when I multiply by. Then we can go through our process. Distributed property. 5x plus 12x plus 60,000. Okay? The numbers are much bigger, but they're on the same scale of magnitude. So it's really not that much extra work. I can combine these terms. Fairly simple. I can subtract 60,000 from 94,000. Well, the thousands all line up, so it's just a matter of 94 minus 60,000. And then we'll rewrite that a little closer together. Divide by our coefficient. Okay. 34 divided by 17 is 2, and then I've got 3 zeros left over. So larger scale of magnitude, but much, much easier to deal with.